Hello everyone, welcome back to this algorithm with Python series, and in this video we are going to discuss BFS, which is known as breadth first search. Okay, so we will discuss that how this algorithm actually works and for which data structure we use BFS, and with which data structure, with the help of which data structure we actually implement this. So first of all, we need to understand that this BFS algorithm, it works on graphs and it works on trees. So if you want to search something from graph or tree, which algorithm you can use, which is the optimal algorithm, and that is called BFS right here, and its full form is breadth first search. Now let's just go ahead and quickly create a graph in which we can use an example to learn BFS, that how it works. So let's say we have this A. I will remove this. We have this A. We have this B, C, D, E, F, G, and we have H, and they are connected like this. So this is a graph based on 8 nodes, which we will use to understand BFS. Okay, I'll just switch to full screen so we can see it more clearly. I will simply go ahead and change this so we can understand that it's a D instead of a I. Okay, so suppose A is our source node. We say that A is our source node. That means it has no parent nodes, so its parent nodes are null, right? So as it is a source node, then its level is 0. So what is level? Level, in other words, is simply distance of two nodes, right? So obviously the distance of A from A will be 0. In other case, if we talk about B, then B is one step away from A, right? So that means its level will be 1, or the distance will be 1. And if you talk about C, then C is 2 steps away from B. B is a neighbor of A, and C is the neighbor of B. So it is a C is a neighbor of neighbor of A, right? So it exists on 2 steps. So the distance will be automatically 2. Means this one plus this one. So 1 plus 1, it will be 2. And same goes for D. The level is 1, and E and F level is 2, and G and H is level is simply 3. Right, so I'll just go ahead, and for now I will remove all of this, and we will see that how we can implement our BFS on this graph. So first of all, what we need to understand is we need a queue to implement our BFS on this graph. Queue will help us in moving from one node to another, and we also need another dictionary, another data structure that we can use to keep track of all the nodes that we have visited, because we do not want to visit a node twice. So let's just go ahead and create 2 dictionaries. Let's say the first one is called visited, and the second one is called queue. So queue is the data structure that we will use for which will help us in moving from node to node. I'll simply remove this, and we can quickly take a look at what is a queue. So queue is a data structure that looks a little like this. So it's like a stack, but the only difference is it's based on FIFO, and FIFO is first in first out. Suppose you give a stream of alphabets to a queue, A, B, C, D. So you entered A first, right? So if you pop an element from this queue, then A will be popped in the first place because A was entered first. Then B will come, then C will come, then D will come. So the first element that you will add will pop out first. So that is called queue, and that is the only difference between stack and queue. Okay, I'll simply just remove that, and we will again come towards BFS. So we have a dictionary called visited, and we have a dictionary call, or we have a queue that will keep track of all the nodes that we have visited. Okay, and we will initialize both of them with A. A is a source node. Now here you have to understand what here you have to listen to me very carefully, that how this queue will help us in moving from one node to another. So we have A in this queue, right? The very first thing that we will do is we will pop that A from this queue. Now what is meant by popping A from queue? It means that when you pop A, the neighbors of A will be added to this queue. So in this case, the neighbors are B and D. They can also be other way around, like DB. I mean, we don't have to write them in sequence like BD. You can also write them DB, but I've simply just written BD, so it really doesn't matter. Okay, when you pop an element or a node from queue, its neighbors will be added to that queue. So in this case, we have B and D, right? When you pop an element from the queue, that element gets added to a visited dictionary. That means we have already visited this node, right? So we have A here. In the next iteration, what will happen? We will pop this B. When B is popped, its neighbor C will be added to the queue, and B will be added to visited because we have visited this B node. In the next iteration, we have D, so we will pop D, and its neighbors E and F will be added to the queue. And because we have popped a D, so this D will be added to visited. In the next iteration, we will pop C, and C has no neighbors, so nothing will be added to the queue, and C will be added to visited because we have visited this node. In the next iteration, we will pop E. This E will be added to visited, and its neighbors are F and G. Now F is already in the queue, so we will not add it. We will only add G here. In the next iteration, F will be popped, and this F will be added to visited, right? And its neighbors are E and H. Now E is already present in visited, so we will not add it. We will only add H into the queue, right? In the next iteration, we have G, and when you will pop G, then this G will be added to visited, and its neighbors are E and H. So E is already present in visited, and H is also present in queue, so we will not add anything. In the next iteration, we will pop this H, and this H will go right into this visited dictionary, and its neighbors are G and F, and G and F, they already exist in visited, so we will not add anything new. And that's how your queue and your visited will be completed, and your entire graph has been I mean, you have traveled through entire graph, right? So suppose if you want to find G from this graph, and you can see that we have visited all the nodes A, B, D, C, E, F, G, H. So you will definitely find where G is, right? So that's why we can use BFS to find something, to search something in a graph or a tree. So suppose we were talking about G, and you want to find that what is the distance of G from A. Then how will you find the distance from G from A? Earlier we discussed that the level of A is 0, and I said that the level is just another word for distance, right? I'll simply just go ahead and minimize it a little bit so we can see it a little more clearly, I will just okay. Now, so I just said that level is just another word for distance, right? And for A, we have a level of 0. So how the distance or the levels are decided? They are decided step by step. For example, the neighbors of A are B and D. They are one step away from A. So we can give them B is 1 and D is 1, right? And C is the neighbor of B. That means C is 2 steps away from A. In other words, one step of C plus one step of previous node. So 1 plus 1 will be 2. So the level of C will be 2. And same goes for E and F. E and F are neighbors of D, so it will be 2 for E and 2 for F. Okay, we'll write 2 for F. And same goes for G and H. G is another step away from A, so 1 for G and 2 for E, so 2 plus 1, it will be 3. And same will go for H. Right? So these are the levels that we have decided. So that means if we were talking about G, we were finding G, and we were finding that how much was it away from A, then we will say that G was 3 levels away from A, right? So the distance between G and A is 3. So that's how you can find the distance of 2 nodes. There's another way to explain this. For example, we were finding G, right? So whenever you reach the node that you're looking for, in this case it's G, after that you go to its parent nodes. You see that how many parent nodes it has. So in this case we have one parent node E, E's parent node is D, and D's parent node is A. Sorry, D's parent node is A. So 1 plus 1, 2 plus 1, 3. So 3 is the distance of G from A. So that's how you can find the shortest distance between G and A. Okay, so BFS is the most optimal way to find or search something in graph or tree. It is the most optimal way, and its time complexity TC is big of V plus E. Here V is vertex or node and E is edges. So these bubbles are called nodes or vertex, and these lines between them, they are called edges. So that's it about BFS or breadth first search, that how this algorithm actually works in theory. In the next video, we will go ahead and implement this algorithm using Python.